it here, and the floor is yours. Thank you.
Okay. Thank you, Christine, for your nice introduction. And I'm Yuanzhuo. Today, it's really an honor for me to have this opportunity to share my work. And today I'm going to talk about the Chiral three-nuclear force, as Christine mentioned, and the continuum in weakly bound nuclear systems. To be honest, the main content of this topic was accomplished by 2020 when I finished my PhD thesis. From then on, I start my postdoc career and join the nuclear lattice effective field theory collaboration and move my main focus to the lattice calculation. So I would also like to take this opportunity to give a brief introduction about the recent ongoing progress about that. So first, by the way, any suggestions, comments are welcome. So you can please stop me if you have any. So first, I will show my thanks to all my collaborators, Professor Furong's group in Peking University in China, and Luigi Coraggio, Angela Nunzio from the NLEFT, Italy, and Professor Nicolas Michel from IMP. Also, Dr. Simi Wang, I know he was working in MSU for many years and now a faculty in Fudan University. Dr. Baishan Hu and Zhonghao Sun from Triumph and Oak Ridge. Of course, I want to show my thanks to all the collaborators of nuclear lattice effective field this series collaborations, which achieved quite a lot of success, and which was led by Professor Din Li. So we know that atomic nuclear is a self-bound quantum many-body system, and as we adding particles, protons or neutrons to its limit, this self-bound system will become weakly bound weakly bound or unbound. At that region, the particular phenomenon like halos, narrow resonance will appear. All of this attract quite a lot of interest, not only from the big experimental facilities, but also from the complex theoretical calculations. One famous anomaly is oxygen dripline, which was pinned down around 20 years ago. And from then on, people are working hard to explore more about this neutron-rich region. In 2012 and 16, people observed the nearly unbound oxygen 26. A big breakthrough happened very recently, just in 2019. The neutron dripline position has been experimentally confirmed up to fluorine 31 and neon 34. Moreover, a two neutron halo has been measured in 2020. Besides that, there are many other exotic phenomena like helium-6, helium-8, and a new experiment just in the last year has measured the inner structure of the boron 11. This is a Borromean nuclear and also halo nuclear. On the other side, the new proton-rich side also exists exciting progress as a major symmetry of the halo lithium 11. Oxygen 11 was observed in 2019, and unbound magnesium 18 has been observed in 2021. All of these new observations and discoveries has also put forward to new challenges and requirements to our theoretical calculation. On the one hand, this nuclei actually belongs to the open quantum system, so that the continuum effect could play an important role. On the other hand, recent studies have shown that three nuclear force could be crucial, not only for the binding energy nuclear saturation point, but also for some structure of low-latent states. One typical example is a Borromean's ground state. It can be reproduced only after including the three nuclear force. So in this talk, I will concentrate on these two aspects, chiral three nuclear force and the continuum. So the outline will be the discussion of chiral three nuclear force first, and then move to the continuum effects. At last, we will combine those two together and study three interesting or particular cases which belongs to the weakly bound nuclear systems. We know that proton or neutron are not fundamental particles, but constituted by the building blocks and the other building blocks, which are the quark and gluon. But hopefully, with the development of effective field theory, the physics of different degree of the physics of different degree of freedom can be linked by each other. And at this level, the nuclear physics can be linked to the underlying theory QCD by chiral effective field theory. So in general, this kind of effective Lagrangian can have infinite many terms. To make this theory manageable and calculatable, we need the help of chiral perturbation theory, which can organize those terms order by order and according to its importance. It considers the degree freedom, its nucleons and pines, also respect the chiral symmetry and its breaking. One remarkable feature of this is the many-body force will appear and will be treated on an equal footing. For example, at the next leading order, the chiral three nuclear force appear, and it contains 5 low-energy constants. 2 of them appear at the first time, and they cannot be fixed by fitting the nuclear scattering phase shift, but by some other observables of helium-3 or helium-4. It should also be mentioned that the chiral 2 nuclear force have been developed and widely used at the early of this century. But due to the complexity of this three-body force, it is only recent years people can introduce this chiral three-body force to our nuclear many-body method. By the way, this chiral three-body force is one we are going to deal with. So what we want is to express this three nuclear force into the harmonic oscillator basis. Then they will become the matrix element which we can use. Once we have that kind of tools, we may have the ability to study its properties and its effect in finite nuclei. Now we are going to what we are going to do is fill the gap between those three nuclear matrix elements and those three diagrams. In general, it needs 3 steps. First, we need to transform the basis from GG coupling basis to Jacobi basis, during which procedure the center of mass, the degree of center of mass will be separated. Since the matrix elements need to be anti-symmetry, here we diagonalize the anti-symmetries to make it anti-symmetry. And at last, we need to calculate those 3 diagrams in Jacobi basis. In formula, it has this kind of structure with some transfer coefficient and the matrix element in Jacobi basis. But to be honest, this is not a trivial work, both in deriving formula and making codes. For example, the 2-pi exchange term has a very complex tensor structure. After some derivation, it could be looks like this. And for each Jacobi configuration, Jacobi state, it has many summation, which the range, whose range could be different as we changing the configurations. Also, there is in the kernel of this formula, there exists high dimension integration with many indices. What's more is in practical real world calculation, we need quite a lot of this kind of matrix element to build for our JJ coupling basis, JJ coupling 3-body matrix element. To tackle this kind of difficulty, we need to make our code more efficient. Generally speaking, what we have done is to reduce redundant configurations as much as we can and reduce redundant computation as much as we can. For example, all of these CG coefficients, 6G or 9G coefficients, actually they can be calculated beforehand and store it to the memory and load it when we need. Similar similar strategy can also be used in this high dimension integration. Of course, to use more computation resources, we need here we adopted the hybrid OpenMP and MPI to parallel our codes. And with this, all of this optimization, we can generate the 3-body matrix element around the E3 max around 8 or so. And later on, we found that if we add some the cut of total moment, the angular momentum in Jacobi basis, the ability of our code will increase quite a lot. After having obtaining the 3-nuclear matrix, 3-nuclear force matrix element, we can add it to our Hamiltonian. But it's also difficult. It's still difficult to deal with it directly, since it is compared to the 2-nuclear force, it has more indices. Sorry, it has more indices, 3 incoming and 3 outgoing. So alternatively, we choose normal ordering procedure, which can considering the 3-nuclear effects to 1-body and 2-body sector. For the many-body method, we choose the realistic shell model, which is also called the many-body perturbation theory. The key idea is to reduce the full Hilbert space diagonalization to a relatively small model space by introducing a similarity transformation. And once we find this kind of similarity transformation, we can do the diagonalization in a very small model space. Suzuki and Lee proposed such kind of transformation may have this kind of type. And after some derivation, we get this recursive equation. This recursive equation can be evaluated, can be solved by some iterative techniques like KK or EKK. But all of them are based on definition of Q-box vertex function. To solve this or evaluate this vertex function, we performed perturbation expansion. Those diagrams you can see are 1-body diagrams up to 2nd order, and those are the 2-body one up to 2nd order. If we go up to the third order, it in total have around 126 diagrams. More details can be found in this reference. So equipped with those tools, we can do some real-world calculation. Here we choose the light P shell nuclei for our testing ground and benchmark with local shell model calculation. Among those figures on the left column is our result with and without 3 nuclear force. Experimental data was put in the middle, and the calculation of local shell model was put on the right. We can see that our result gave reasonable result compared to the experimental data and local shell model calculation. What's more is in the beginning, I mentioned the Borromean story, which the need of 3 nuclear force. Luckily, we can tell the similar story here. That is, when we include the 3 nuclear force, the right spin information will be given for this Borromean ground state. After talking about the generating and benchmark of current 3 nuclear force, we may start to talk about something about the continuum effects. We can add nucleus, as I mentioned before, we can add protons or neutrons to a self-bound nucleus to its limit. But just like liquid drop, it has a limit. And where one more particle ion will break down the system. That was also called the nuclear dripline. Around that region, the nuclear belongs to the open quantum system. So the conventional choice of a harmonical oscillator basis cannot to obtain or include the information from the outside. But if we choose a potential with finite dips, we may have that kind of opportunity. So according to this idea, Berggren basis has been proposed around the 1970s. It generalized the one-body Schrodinger equation into the complex K-plan, which can create the bond, resonance, and continuum states, single particle states on equal footing. Of course, different kind of state have a different asymptotic behavior. There were several methods based on this Berggren basis, and they achieve quite a lot of success. What we want to do is taking advantage of the Berggren basis and combining it to the many-body perturbation theory, which we discussed it before. And from that framework, we can use chiral force to study the weakly bound systems. So the workflow will look like this. First, add the 3 nuclear contribution to the Hamiltonian, as discussed before, and then transform the Hamiltonian to the Berggren basis, where the continuum effect will come in. To get to obtain the effective model space effective Hamiltonian, we need to calculate the Q-box, so-called Q-box folded diagrams in complex K-space. And at last, we can do the diagonalization procedure with the Jacobi-Davidson method. So after talking about the whole framework, we may move on to the calculation of weakly bound nuclear systems. Here we choose 3 of them. And the first one I want to talk about is neutron-rich oxygen isotopes. In this work, we calculated the ground state, their ground state energy respect to the oxygen 16 core. The right line is the calculation with 3 nuclear force, and the blue line is our Gamow shell model calculation without 3 nuclear force. From the comparison, we can see that 3 nuclear force may have a repulsive effect, and these effects will increase as we increasing the particle number. This red line, which including the continuum and the 3 nuclear force, will give the right, will give the unbound oxygen 26, which implies the right oxygen isotopes. The tripline position is oxygen 24. So since this Chiral's 3 body force at the next leading order has 3 terms, we want to analyze the effects separately. So here we draw this sub figure, which we add these 3 terms onto the calculation with only 2 nuclear force, and we can find that the 2 pi exchange and the contact term will have repulsive effects around this region, and for the 1 pi exchange term, it has some attractive effects. The interesting thing is that the 1 pi exchange and the contact term have similar absolute value, but the opposite effects, opposite sign. So the net effect almost canceled out, and leaving the 2 pi long range 2 pi exchange dominates. A more discussion and calculation can be found in this reference, this paper. The second one I want to talk about is this particular nuclear is a Neon-17, which located on the proton-rich side. And it is a Borromean nuclear with unbound fluorine 16 subsystem. The calculation shows that 3 nuclear force may play a crucial role for the unbound fluorine 16, which makes Neon-17 the Borromean structure. This Borromean has some may share some similarity as helium-6, which is a halo nuclear. So we did the calculation of the we calculated the 1 body density in model space of this Neon-17's ground state. From the comparison of the right and the blue dashed line, we found that actually the 3 nuclear force have little influence on the density distribution, while from the comparison between the red one and the purple one, which we do not include the continuum, we found that the continuum plays an important role, especially for this at a large distance, and this density distribution at a large distance also suggests that the Neon-17's ground state may have some halo structure. To study it more, we also calculate the correlation density, the proton-proton and the proton-neutron correlation density. From the comparison, we can find that maybe this halo structure could be a 2 proton halo, and more details can be found in this reference. The last one I want to talk is a recent progress, which was led by the collaborators in Peking University. Before, we always use Wood-Saxon potential to generate. Oh, sorry, I forgot to mention that before the Berggren basis was generated by Wood-Saxon potential, and of course we have another options like we can use Hartree-Fock potential. So that was also called Gamow Hartree-Fock. To get this Gamow HF basis, this basis, we first need to solve the HF equations in real space, and then extract this HF potential. One can also write down it into a complex K space. At last, we need to diagonalize this Gamow HF one-body potential and get the Berggren basis. One obvious benefit is that this method can get rid of the dependence of Saxon parameters. Also, the three nuclear force can be included naturally when we build the HF potentials. So this time we choose another system to study, which is oxygen-19, and its major symmetry partner sodium-19. If we exclude they are major symmetry nuclei. So if we exclude the Coulomb force, we can say from those two columns that they actually behaves quite quite similar, shows quite good major symmetry. But they cannot get the right ground state and the first state spin information. If we include the three nuclear force, that situation could be changed. What's more is in experiment data, they found pronounced Thomas-Ullmann shift. That is the first compared to the oxygen-19. The first one half plus state has dropped quite a lot, which the mirror symmetry has been broken. Of course, the Coulomb provide a major contribution, but surprisingly, the continuum also could make a significant contribution. One may find some clue from the configuration of this state, which has a large S-wave component. Due to the lack of centrifugal barrier of this S-wave state, that causes a leakage of the wave function, which means Coulomb repulsive energy could be much smaller than the other state, like the 3/2 state or 5/2 state. That also means a gap between them will be smaller. And more discussion and calculations could be found in this reference. As I mentioned before, I also want to take the last, before the end, I want to take some of time to give a brief introduction of our recent progress on the nuclear lattice effective field theory calculation on the finite temperature neutron matter systems. More precisely, what we are interested in is structure factors of neutron matter at a finite temperature that will determine the neutrino-neutron cross-section in the supernova explosion. That is also the one of the key information to understand this grand astronomy process. So an initial calculation could may attract a lot of interest. To perform such a kind of calculation, we may need the help of a pinhole trace algorithm, which was first developed in 2020. The key idea is that the canonical partition function can be expressed using pinholes, and these pinholes or the configurations can at last be summed up by Monte Carlo sampling. And with this method, we may have the ability to describe the neutron matter at a finite temperature. So with this pinhole trace algorithm and some other development, we did leading order calculation, which share some similarity. This preliminary result shows some similarity to the newest simulation. And what we can do in our framework is that we can include also the higher order interaction by perturbation. So we developed the perturbation to the wave function. The method to achieve that, we developed the perturbation to the wave function, and also the so-called rank 1 operator method for the observable, for measuring the observables. I may skip these details, but I'm really happy to discuss it afterward if anyone shows some interest in about this. For this method, there is this disadvantage or is a challenge is that it needs quite a huge computation effort compared to the traditional of the original one method. If we want to measure some observable at time slice compared to the previous one, we actually need to do around 16 times, let's say L3. L is lattice size of times of effort to do that kind of calculation. So this time we move to the help of the GPU, and I started this coding task around 5 months ago, and this procedure is almost done, including benchmarking and optimizing around 1.5 weeks ago. To be honest, those kernels, GPU code behaves pretty well. They can use diverse quite well with around 80 to 90% average percentage of the usage, and the cost of memory transfer, the cost of memory transfer from the CPU side to the GPU side is quite small. You can see from this profiling data. For some testing Hamiltonian, we can achieve around 60 to 80% times speed up, and for the real world Hamiltonian, which we are going to use for our neutron matter density correlation function calculation, it has impressively 190 times speed up. So next, what we want to do, what we need to do is to generate that kind of data at the N3RO. Of course, sorry, even though it has quite impressive speed up, the time and the computation resources also is huge. This is only for the test, and for real calculation, we need times around 50 or so. But anyhow, we think that we have the chance to get that data to perform that calculation. So I may stop here and make a short summary. We first derive and calculate the 3-nuclear force and its matrix element at next to leading order to test the reliability and benchmark. We choose a light p-shell nuclear, and we found that consistent with the other calculations. With the help of Berggren basis, we can introduce a continuum effects to our many-body method that allow us to do the calculation in weakly bound nuclear systems. and to study the roles played by three nuclear force and continuum, we choose three systems to study. And as an improvement, we are going to include, we are thinking to include the higher order contributions. And since there were many interesting stuffs around the triplet region, following this approach, we are going to explore more, like the neutron dripline, the heavier system like the dripline of Borromean Ne. We also discussed later about the nuclear lattice EFT calculation of the neutron matter calculation. The leading order calculation shows some reasonable results. And we have developed some new method, technique, and code to do the high order perturbation, hoping that could help to give a good description of the neutrino-neutron scattering in astronomy process. Okay, so I think that's all, and thank you for your attention.
Thanks a lot. That was a great talk. And I enjoyed it. Any questions? Just raise your hand here in Zoom, and then I'll just go through the raised hands. So in the meantime, just to break the ice, if there is ice. So you mentioned a 200 times speed up on one of your slides, right?
Yes.
How do you get this actually? Could you be a little bit more specific? So is this just plain matrix multiplications or matrix vector or matrix operations? You mentioned plus and q plus here. I'm just being curious.
That is yes, of course, we need to use a q like cu plus, like q plus, but more than that, actually we need to optimize the kernel by kernel. There are many other strategies. Maybe I can show one example is that we found the task we meet is we need to, at each calculation we need to do the small matrix element, but quite a lot of them at the same time. But we found that if we use CU plus, it's not so efficient. But if we change the double precision to float precision, it is impressive. I mean, I can show this figure. This sorry, maybe this one to you. That you can say this double precision. It can only achieve 0.5 teraflops, but if we change it to single precision, it can achieve 13 teraflops, which is a huge difference. And also the final result does not see the difference. So a lot of this optimization considering which can help to achieve that behavior at the last, which you mentioned is around 200 times speed up.
So in summary, it's because you use floating point arithmetics and so it's basically linear algebra operations, right? So that's the answer to my question. Is that right?
Yes.
Okay, good. Vitek.
Hi, very nice talk. I would like to understand, how do you recalibrate the parameters of your chiral force when adding continuum space? Because parameters of your forces, right, must depend on the actual space in which you do calculations. You add lots of continuum space, so the forces change, right?
Actually, for the chiral force, we just use the chiral two-body force from Professor Mahalit's chiral two-body force, and for the three-nuclear force, the two parameters, low energy constant, we take it from the Professor Navacho's paper, and we do not make the change. So, and the other parameters are, for example, to generating the Berggren basis, which is a Wood-Saxon potential. So that's all. And for example, in the oxygen, in this work, we just take the how to say, the universal parameters of the Saxon parameters to get the Berggren basis. Is that your question? I'm not sure.
Okay, I understand, but in principle, you should do recalibration of the parameters every time you change the space. Okay, thank you.
Okay, thank you. Thank you for your question.
Thanks, Vitek. Next one.
So maybe I just address the question maybe to the speaker,
Yeah, go ahead.
also Vitek, since Vitek bring this up, right? So what actually is the traditional approach to recalibrate interaction on a chaining basis in all these exponential Berggren based calculation?
Sorry, can you repeat it?
Okay, yeah. So Vitek asked the question about how to recalibrate the underlying interactions when you change the basis, right? Even just within the Berggren basis framework. So I didn't appreciate this question. What was traditional approach? Did people actually start doing these recalibrations?
I don't know.
So, Celine, we usually calibrate the interaction. Okay, anytime we change the basis, you add continuum space.
Yeah.
Then, of course, obviously, binding energy would change. It's extremely important in such calculations that thresholds are reproduced, energy reaction thresholds, right?
So you're calibrating against the many body absorber, not against the nucleon scattering.
No,
or
many
few body property.
No,
okay,
yes,
so
you calculate oxygen 28. So you would like to be sure that your threshold for 2 or 4 neutron emission from oxygen 28, right, is right, or 26.
well, yeah, that could improve things. I was thinking like calibrate underlying nuclear interaction and to the phase shift of say nuclear 3.
Well, phase shifts are just 2 body effects. I had primarily in mind three neutron force, 3 particle force, right?
Okay.
So Heiko, well, Heiko is next, but Shilin, you got your question answered?
Yeah, thank you. Like,
okay,
thank you
great.
for the comment. Thank you. Yeah.
I mean, this is maybe also more of a comment. So I'm actually not sure whether in many of these chiral calculations there was a readjustment of the 3-body force. Because usually it's the if I remember, like I think Gauter's paper and some of the others, I mean, I think they essentially used the CD and CE that were determined in the bound state calculation in some way, and I don't think they readjusted that when they went to the Berggren basis. I mean, I agree that in principle, if you make an adjustment and you have continuum degrees of freedom, then consistency would suggest that you should be doing the adjustment in the most complete basis that you can get, and that will have an impact on the or could have an impact, let's say, on the CD and CE without having done that before. But I don't think this has really been explored in ab initio calculations.
Yeah, and this is actually very important as we see in the figure, right? Because adding continuum makes system more bound, while 3-body forces, standard 3 chiral forces, right, are repulsive for those neutron-rich nuclei. So there is a very subtle interplay between those 2 effects.
Okay, so thanks, Vitek. Thanks, Heiko. Any more questions? Okay, then I think we can call it a day, or a seminar to be more precise. Thanks again for the nice seminar. And so our next seminar is going to be, let me look it up here, on April 12th. So I'll see you there. And in the meantime, take care and bye.
Bye. Thank you all.
Thank you.
Bye-bye.
Bye.
Thanks, Yuanzhuo. Very, very nice talk.
Thank you. Thank you.